So there'll be a break after a few talks. But our first speaker is Antonio Negretti from Hamburg.
Thank you. Thanks to Tommaso and Svetlana for organizing this workshop and for giving me the opportunity to tell about our recent work. And I probably contrary to most of the people here, I enjoy also the weather because staying in Hamburg, I almost forgot how it's summer there, how I should like. So I really enjoyed the heat of outside. So I'm going to talk about atom-ion systems. Here I just give a short overview because also has been already told by Tommaso and Peter before. So there are several theory works on this subject, how to use these combined systems. Originally, this field has been already started in the 60s when Eugene Grossa was trying to understand, to provide a microscopic theory of why ions were had this small mobility in liquid helium, where he made these ansatz for the bosonic system in order to describe the condensate when there is an impurity inside, ionic impurity inside. And then in the 2000, to say this with the advent of cold atoms and this field has gone slowly at the beginning and in the last year quite rapidly. There were proposals for quantum information processing, as Tommaso was telling to you this morning, also for investigating boron physics, also to use these systems of ions to probe quantum correlation in a quantum gas, and so on. From the experimental side, probably it's not complete this list, but there are already experiments working with these combined systems. They didn't reach yet this ultra cold regime where most of the theory proposals rely on, so they mostly investigated collision at the moment, and there are different trap technology that they use for trapping the ion in the condensate. Most of them rely on the combination of Ball trap technology, so radio frequency traps with typical trap optical techniques for cold atoms. A new direction that is pursuing in Germany within Tobias Schätz's group is optical trapping of ions, which has recently provided quite interesting results in this respect. So there is a bunch of activity in this field now. Let me, so at least provide you a motivation why we are interested in this business, mostly for quantum technology, quantum simulation purposes. So-called atoms in optical lattice, for instance, are great systems to investigate condensed matter problem. They have shown main experiment that this can be the case. They are easily scalable. They have, depending on the atoms that are trapped in the optical lattice, can be bosonic or fermionic. On the other hand, these systems doesn't have phonons because of the classical potential of the optical lattice. So it's much more difficult to engineer a long-range interaction that are typically not natural solids, so to say. And somehow, to some extent, are more, compared to trapped ions, more difficult to control at the single particle level, I would say. On the other side, so trapped ions have been proven to be a great system for quantum information processing in particular. So they have reached really astonishing fidelities, at least in 1D systems. So this readout and control of single ions is very well established now in the atom in the ion community. So they have naturally long-range interactions, so because of the Coulomb interaction, and so they can mediate, so engineer phonomediate interaction. So on the other hand, this system is more harder to scale up. So there are proposals for two-dimensional ion crystals, but it's still an open question, so to say, how efficient to scale up this system. And then they do not have naturally fermionic statistics. There are possibility to mimic this, but involve a number of gates that are not easy to implement, so to say. So we want to combine these two worlds together in order to get the best of them, of each of them, in order to have a unique platform in that sense for doing quantum simulation, for instance, research. So on one side, as I said, we are interested to use this combined system for quantum information and simulation purposes. Here we show how this 1D string of ions in interaction with linear with 1D quantum gas can be used, for instance, to mimic the pilot instability in solid. And then, as Peter was telling this morning, also to investigate impurity physics in general with this kind of system. So one could also consider neutral impurities, but the interplay between the different lengths and energy scales make the system kind of unique. So this is the outline of my presentation. So it's divided basically in two parts. Most of it will be concerned on how to engineer laser controlled atom-ion interactions, and then I will briefly tell you about our recent investigation on how to use also this system for studying confinement-induced resonance, for instance, in reduced dimension. Okay, so let me start with this topic first. So I will first introduce what is the atom-ion interaction. Although I think it would be not necessary, but so if you have a free atom in space alone, so and you put an ion nearby, this atom gets polarized. So then the interaction, because of the presence of this ion of this electric field, induces this dipole of the atom. So the actual atom-ion interaction at long range distances behaves like this. So it's basically the interaction between the electric field of the atom and the dipole moment. And these parameters depend on the polarizability of the atom. Yes, if you add also the centrifugal barrier on the top of this atom-ion interaction, you get at least for L equal to 1 for the first partial wave, this kind of potential. So basically you can identify two typical energy, so two typical parameters of this potential. So the stars, which basically as a rule of thumb provides you the onset, so to say, of S-wave collision, so to say. So below this energy you should enter in this ultra-cold regime, and this air star typically gives you the interaction strength of this, so interaction range of this atom-ion interaction. So to give a few numbers here for typical ion atom species. So here that are typically used in experiments. So you can see that this air star interaction, if this could be thought as the typical atom-ion scattering length, is on the order of a few hundred of nanometers. That has to be compared to typical neutral system where they have a few nanometers. So in that sense, it's kind of long-range interaction. And also the typical energy scales that are involved. So if you look at the temperature here, is much smaller than compared to the neutral scenario. So it somehow is also more demanding for experimentalists to reach this S-wave collisional regime. So there is a nice review here, and just let me advertise shortly that probably next week we are going to submit also our review. If you are interested also to get your feedback on our review, ask Michał Tonza, who would provide you eventually a copy of the review, and it would be interesting to get your feedback on that. Yes. So now the micromotion. So the point is that we wanted consider ions that are trapped in the time-dependent fields, and there is this technical issue called micromotion that might prevent to realize this nice theory model that I was listing before. So now, without entering many details, so if you have typically 1D linear trap, pole trap, with this kind of characteristic parameters, basically geometric parameters. So the classical trajectory for an ion inside of this pole trap is given by this equation. So by this equation, just by solving Newton equation of motion. And typically what the people do is to neglect this second term, so you would get just this red line, so you have this perfect harmonic behavior, oscillator behavior, which is the typical approximation of this so-called circular approximation for considering basically an ion trapped in a harmonic trap. So this is because typically this is on the kilohertz range, whereas this is on the megahertz range. So typically one neglect this, and if you do not neglect this, you see that on the turning point of the ion motion, you have on the top of the harmonic oscillator of the harmonic oscillation also this quick oscillation on the top, which might cause in that heating in the neutral system as well. So, so now from a classical perspective, so this was with a single ion without an atom inside. So if we are even in the ideal case that this ion is prepared in the center of the trap, where you don't have any feeling of the external, so time-dependent electric fields. This ion stays there, although I mean quantum mechanics has a given width. But now the point is, if you put the ion, sorry, an atom nearby, because of this long-range atom-ion interaction, you can compute classically the trajectory, and you will see that depending on the atom that you choose, this ion will be displaced from the ion trap, and then it will start to oscillate, and so in that sense get it heated. And the lesson that one can learn from this simple calculation is that it is better to choose lighter atoms than heavier one. So it's a good, so to say, strategy to choose a heavier ion and a lighter atom. So we have checked, so this kind of prediction results have been obtained already by several people, both from a kind of quantum mechanical perspective and a classical one. We have also found the same kind of results if you have a double well potential, as Tommaso was discussing this morning. So and you can, so without entering now here in details, but so these are basically the matrix elements that couples different states of the atom and the ion motion for the micromotion Hamiltonian, and you can see that if you choose this pair, the strength of these matrix elements is much larger than in the case of lithium deuterium. So again, so as has been pointed out by several people, it is a good strategy to choose indeed a lighter atom and a heavier ion. In that sense, you can then also have this state-dependent tunneling through the barrier. This kind of robust, and you can also again choose distances that are not too close between the two systems, so that this effect is minimized. Okay, yes, so as I was telling you right now. So, but if you, another point is just to say that there is another possibility to trap ions, or like via optical fields, as I was saying. So recently has been shown that one can reach even hundreds of milliseconds lifetime, but it's still, in my opinion, not yet clear what would happen if you would have atoms nearby. So this is just for a single ion, but yeah, it might be that this kind of picture will change if you would put an atom nearby. So we still insist with our pole trap, and basically, as I was saying before, and as has been already shown this morning, the basic idea is that instead of consider the atom in the ground state, to consider the atom in a Rydberg level, because then the polarizability scales with this scaling factor, so the n principal quantum number, and in that sense it can enhance quite strongly the atom-ion interaction by just exciting the electron to a Rydberg level. So we basically, in this work, we perform a kind of precise analysis of a single ion in a pole trap in the presence of an atom, and we investigated somehow the impact of the ion motion when the ion is excited to a Rydberg level, the atom is excited to a Rydberg level. So we solved these three-body problem, so to say, with the single electron and Rydberg electron, the core, and the ion, and in the presence of the electric fields of the pole trap. So one can find, at least along the zeta direction, so the longitudinal direction, where there are no type-dependent electric fields, a minimal distance where the electric fields of the ions and the electric fields of the pole trap are compensate each other, so that at that point, this distance basically there is no electric field, so to say. So the point is that if you are below the distance is below this quantity here, then you can basically neglect the impact of the electric fields of the pole trap on the Rydberg atom. So if you plug some numbers, so our goal would be to reach micrometer distances where to put the atom and the ion separation, and so basically one can under this assumption, basically one can assume that the detuning is given by the bare detuning, and then just the electric field of the induced by the ion. So we can forget about the electric field of the trap. So we have performed this analysis quite carefully. So these are it's the energy spectrum that you would get for lithium and ytterbium. So as a function of the separation between the two systems, so to say. And one can see that if you dress so if you would excite the atom to this level here, this Rydberg level, you can also basically approximate quite well the atom interaction by using second order perturbation theory, by just replacing the C4 factor with the corresponding Rydberg polarizability somehow. And this works quite well up to distances of 500 nanometers. So one can indeed then think to put the atom and the ion at a distance that is about 1 micron, and get an effective large interaction between the two systems. We have, so this was without including the electric fields of the pole trap. We have also checked that this is true. So here the three circle means basically in the presence of the time-dependent electric fields at 3 different amplitudes. So the blue, it means one is at the maximum positive amplitude, and the red one at the minimum one, and the yellow, so the green one is basically zero, and you see that it's basically the influence at these distances is practically negligible. So the impact of these electric fields is basically negligible, as also shown here in the insert. Okay, so then now when we have learned about this, we can imagine basically to the Rydberg-dressed, basically the atom, so where the two, as I was showing before, the levels here are such that, are well addressable, this level here, so that we can indeed solve basically these two-level Hamiltonian and get an effective interaction for the atom-ion system that looks like this. With these parameters here, if you put numbers, you can get a strong interaction at relatively large distances. So 1 micron, you have to compare to the 100 nanometer of the ground state atom-ion interaction. And this is somehow similar also to the Rydberg dressing of two neutral atoms. So here I show you basically the results of this effective interaction, which is controlled by laser fields, basically. This is again for the ground state. This is for two different detuning, and you can see indeed that this interaction is much more long range, and you can indeed in this way hope that the impact of micromotion on the atom is much less detrimental than with respect to the ground state. So now, what I'm going to show quickly is that if you put the atom at a distance such that the potential here is linear, you can indeed engineer this kind of spin-spin Hamiltonians between the atom and the ion. So similar to what is done with trapped ions only. Again, the idea is the following. We put the atom at this particular distance where its potential is actually almost linear, and we basically linearize this effective atom-ion interaction to first order. And then the point is that we have to match the different energy scales between the ionic system and the atomic system. So I remember here is typically on the 100 kilohertz regime, whereas this is in the kilohertz regime. And this has been done by basically modulating the amplitude of this parameter A that depends on the laser fields by modulating this interaction at the typical frequencies of the ion motion. So in that way, one can couple the internal spin state of the atom with the ion motion. This is what one can show at the end of the day. So one can get basically an interaction, an effective interaction between the atom and the ion that depends on the internal state of the atom and the ion motion of into the trapper. And if you now also combine ion quantum processing techniques, so like the Sorensen-Murmur gate for the ion, one can indeed engineer at the end of the day by choosing probably the parameter like in this way. So if both the atom and the ion are in the down state, nothing happens. If they are both in this state, so up state, then because of this choice you can have no motion of the ion. But if the two are in different spin configurations, then you can excite the ion motion and then get this kind of spin-spin interaction in the system. Yes, and then one can show basically that by choosing properly the parameters and the time, one can go back to the initial motional condition of the ion and get a kind of bell state or entangled state between the atom and the ion. And this is a plot where we show where we included also the micromotion in the simulation of this kind of quantum gate between the atom and the ion. And again, you can see that when both the atom and the ion are in different spin states, the ion the motion is excited. So, and then will also affect a bit the atomic motion. But compared to the ground state case of the atom ion interaction potential basically is a significant gain where this micromotion doesn't affect so much the motion of the atom. So with that, I would move to the second part where we ask ourselves, for neutral system, if confinement-induced resonances could appear also in this kind of system. So we were motivated basically because of the work that we did a few years ago about this quantum simulator with the atom ion systems, where we found that the atom phonon coupling was not so strong in the longitudinal direction. So this might be a way to enhance the interaction between the two systems, or between the atom and the phonon in the longitudinal direction. Well, one could also think about to use this kind of resonances to determine atom ion scattering properties, so like the scattering, or even to measure eventually the temperature of the quantum class. I mean, there are other possibilities that are probably much more efficient, but one could be think about is also for this kind of resonance. And then more recently, it might be interesting to look at this for sensing purposes, as also Tommaso was mentioning this morning, and tomorrow I think there will be a talk about that for tonight. So here we consider highly trapped ions. So again, without including the motion of the ion, just in a waveguide. So we have considered fixed ion and then an atom in a waveguide. And we were wondering if this kind of atom confinement-induced resonance could appear. So we basically solved the Schrödinger equation for the atom in a waveguide in the presence of this atom ion interaction by solving this and by using this as a boundary condition for at large distances, basically. By computing, by extracting what are these scattering amplitudes, one can infer what is basically the effective 1D interaction. So in the case so the long wave limit, basically, when R star is much smaller than the transverse width of the waveguide, you would get basically the known results of Bolshani, so that you would have for cold atoms in a waveguide. The nice feature for the atom ion system, so to say, is that given the flexibility that you have to choose this parameter, you can have also regimes in where these confinement-induced resonances might depend also on the mass ratio. Whereas so beyond this kind of limit here. So and an interesting feature also compared to the long wave limit, so to say, is that the width is also much larger than in the neutral also system. So in that sense, one would have more flexibility also experimentally to control the effective interaction. So if you look at the confined-induced resonance position, so by computing basically this relation between the transverse width and the 3D effective 3D atom ion scattering as a function of this parameter here, you can see that you might have, so this is precise the limit at low energies, so at the zero energy limit, where you would get precisely the 1.46 that Bolshani obtained. But again, because of this long range interaction and depending on the species that you choose, you can have so dependence on the actual species that you choose, in that sense more flexibility. And this happens already at trap frequencies of the atom waveguide that are reachable in experiments. And also this kind of effect can be observed at finite collisional energy. So in that sense, is even if you are not really the S-wave regime, I would say one could still hope to observe this this behavior. Yeah, with that I'm done. Basically, so we basically showed that by dressing the atom to a Rydberg level, one can indeed engineer long-range atom-ion interaction that can be controlled by laser fields. And in that way, we provide a possibility to solve this micromotion problem for atom-ion system. One could also engineer atom-ion entanglement, so engineer the spin-spin interaction via the ion motion. And yes, then we have shown with the last part that you can also control the interaction between the two particles via transverse confinement. And yeah, this can basically offer a more broader spatial range of interaction in such a hybrid system. So what one could do is, again, with respect to the first part, look at more many-body systems, so where you don't have just one atom and one ion, but you have really more atoms and ions in a chain, and look at interaction, spin-spin interaction or hybrid spin-spin interaction in the system. One could also try to look at what could happen if you would laser excite the atom to an orbit, so to a non-zero angular momentum states, and to engineer this kind of angular dependent interaction. As has been shown very recently, one could also engineer this atom interaction with laser fields that are repulsive, so in that sense would even make simpler the life of experimentalists. Yeah, and then we are working on the assessment of this of the micromotion of the atom-ion confinement-induced resonances, and then one would also ask if one can get additional controllability by controlling the ion motion in the trap. So if one can get transmission and reflection that depends on the number of one time in the ion motion. So this work has been done not by myself only, but by these guys here. So most of the work that has been done with Rydberg is due to Thomas, and also Alex is sitting here in the audience, and then the second part was done actually by Rydberg. So with that, I thank you for your attention.
Thanks. Question?
In the last part of your talk, when you were talking about the confinement-induced resonance, do you include transfer reactions or associative reactions too?
We didn't consider that, but at least for the lithium-intermediate choice, there is a recent paper, probably will be also followed during this conference, where these charge exchange rates are quite small, so it could be engaged. So in that sense, yeah.
Thanks.
Any other questions? All right, well, thank you. next speaker is Hervé Gaff.
Yeah, thanks a lot. And thanks to the organizers and our host for bringing this workshop together. It's a big pleasure for me to be here. And I slightly changed the title compared to the Book of Abstracts, almost the same content, but I thought that that fits also nicely to this workshop here. Because what we are doing essentially in our experiment is studying dissipative impurities in ultra-cold quantum gases. And this is actually realized with charged particles, as you will see. In our case, these are electrons. So the outline of my talk is the following. I will introduce to you two different effects that can happen when you have a dissipative impurity in your gas. I will show you how this can lead to quantum dynamics in a Bose-Einstein condensate, a special transport property that we have analyzed at the tunneling junction, and that will be important to understand the main part of this talk, which is the defect-induced incoherent and superfluid transport. And that shows you that also when you have a dissipative impurity, you can observe coherent effects, provided your overall system still is coherent. And if time allows, I show you some alternative interpretation of these results at the end of this talk. So the overall idea of this work in our group is that we want to tune and engineer the environment to steer many-body quantum system. And there are various effects or things you can do. For instance, you can prepare certain quantum states. You will see an example, simple example for that. In general, if you have an open quantum system, the dynamics can be well an attractor dynamics, which leads you a nice way to reach the state that you want to prepare here. If you have an attractor state in your system, then it is automatic. It is at the same time the mechanism that stabilizes your quantum state, because if you deviate from the state, you can come back to the state. If you have a small perturbation on that, you will see our dissipative impurity will lead to losses. And if you combine losses with gain, you are in the world of non-Hermitian Hamiltonians, where you have imaginary parts in your effective Hamiltonian descriptions. Another important aspect in open systems is the appearance of phase transitions that you can observe there. And generically, when you have an open system, so in our case, when you remove something from somewhere, you typically induce a transport, and this talk will be about these transport processes, or some of the transport processes that you can observe. Now let me start with what our main dissipation mechanism is, and this is local particle loss. If you consider a 1D system, here atoms tunneling in a 1D system, a leaky optical lattice, then you can describe this with a master equation approach. Here you see the time evolution of the density operator, which has the coherent part, and here it is cut into the environment, described in this Lindblad form here, where you have certain operators here that act on your density matrix. In our case, so in this particular case, where you remove particles from certain lattice sites, these operators are nothing else than the annihilation and creation operators for the boson at each site. And the rate that you have here is the loss rate, so that's the speed with which you remove these particles. And it has been on theory side, considered in several publications here. You will see examples for a modification of this scenario later on, but we will also study the continuous part of it. So if you have a bulk system, and that can now be a Bose-Einstein condensate, for instance, and you have a local impurity, and this impurity just gives you losses, then this will be the appropriate form. And compared to the previous one, you simply replace the annihilation operators with the field operators, and then you have the open system description of that. And if you have now many atoms, as we have in a Bose-Einstein condensate, then you can make a mean field approximation of this. And if you do that, you end up with this equation that describes then your Bose-Einstein condensate here. And you see, you recover the Gross-Pitayevsky equation up to this part here with the kinetic energy, the external potential, and the interaction energy. And what is now new, if you have local losses, is that you have an imaginary potential. So that's the effective result of this. The strength of the potential is directly given by the loss rate and how fast you remove the material from that. Let's briefly discuss what an imaginary potential can do compared to a real potential that you all know. That can be simply studied in a 1D model where you put a complex potential barrier here that has a complex amplitude, which means physically, if that is right, what I told you, there are losses in this region of space from 0 to d with a certain strength, and no losses here and here. And if you just write down this Schrödinger equation with its imaginary potential, you can solve it with a potential, with a normal ansatz, but the wave vectors that you include have to be complex, so they can also become imaginary to describe a damped wave. And then you get, if you look at such a scattering experiment, you have an incident wave from one side and you get a reflected and a transmitted wave that you know from the conservative part, but you also get some missing probability, which is the dissipated part of the wave function. You can calculate the amplitude of all these three contributions, independent of the strength of your losses, so how strong the losses are. And the blue one, first of all, is the transmitted one. That goes to 0, which is certainly not at all surprising. Already a bit more surprising is the red one, that you get reflection here. But at the end, it's a wave phenomenon that you can observe here, right? There is a wave traveling from here in an area where there is absorption. So in the language of electromagnetism, you would say there is no impedance matching here, so and then there is always a reflected part here. And that's what you see, that's the red part here. And for us interesting is the green part, and that is the amount of atoms that you remove, or the amplitude of the wave function that is removed when it enters here this interaction area here. And you see this has a local maximum, and then it goes down. And interestingly, in the limit of infinite potential height here, the green curve goes to 0, which means that if you have infinitely losses, then this imaginary potential barrier acts exactly in the same way as a conservative one, the only result being that there is a boundary condition for your wave function that then has to be 0 at this transition. And the dashed lines that you see here are the corresponding calculations for the conservative potential barrier. So you see, an imaginary potential is not so special, but it has this particular additional branch that can occur, and that will become important later on. Now, what do we do in the experiment? I told you we make a dissipative impurity, and we do this by local losses. And the local losses in our case are realized by an electron beam. There's a focused electron beam, high energy, 6 keV. Whatever the electrons hit is removed from the sample. So it's a pure loss mechanism. However, I think, maybe we can discuss this, that this is quite generic. If you have an ion in a trapped sample and you rapidly shake the ion on purpose, then I can imagine that you end up in a similar situation. If you get a lot of losses, strong losses induced by the ion, and then maybe you end up in a similar situation that is discussed here. So we have this electron beam, which comes from a commercial electron column, and the electron beam does two things. So first of all, it removes particles. Second, a part of the particles is ionized, and these ions are then detected. So we also see the degree of our milling actions here, which is quite useful. The technique has a high spatial resolution, so we can make small defects. For us, it's small in an ultra-cold quantum gas length world. 100 nanometer is a small quantity. We can scan it around, and well, that's essentially the beam diameter here. It's single atom sensitive because we get the signal from every atom, not from every atom, but from the single ions that we produce. We can use this for making images. That was what we had done at the beginning of this technique, which is already a couple of years old. It works in situ, and what will become important later on, it's an in vivo technique, so we can continuously observe the system for a certain time. And at the end, you will see that it's also a nice tool to manipulate and prepare density distributions. Now we can use this. We prepare the Bose-Einstein condensate in an optical dipole trap, and we sum over many pictures, and then we see, for instance, here the density distribution. You see high precision, nice images, and that there is also a high resolution. I can show you qualitatively by showing you these pictures of a Bose-Einstein condensate that has been loaded in a two-dimensional optical lattice here. Each side that you see here has about 80 atoms. Here these lines are pancakes because this is only a one-dimensional optical lattice. And you see that we can not only resolve the lattice sites, but we can also remove atoms from lattice sites prior to making the image. So this is the technical part of what we can do. Now let's come to the physics, what we want to study. The first one is now quantum xenodynamics in the Bose-Einstein condensate. The basic setting is quite clear. We want to create a dissipative defect, so a local loss in an ultra-cold quantum gas. Here it's a Bose-Einstein condensate. Now if we look at the signal over time, then we see that, so what is plotted here is time, and here ions per microsecond. This is the rate of material that is removed from this point here. And this rate first goes down, has some transient dynamics, and then enters into a steady state. And you can imagine this steady state has a balance between what you remove from here and what fills in from here and from here. Because at the end you have a very small defect here, 100 nanometer, and the whole cloud has a dimension of 80 micrometers, so it's about not 1,000 but 800 times larger. So we have a lot of reservoir side, and that allows you to observe this steady state here. But I should mention that maybe at the end of this room here, the signal is also to zero, because you remove the particles, and at the end they are gone. Now I told you that a local loss should be described by an imaginary potential, and that can lead to reflection of the wave that goes into the potential. We have studied this by looking at the overall loss that we observe in the first 5 milliseconds, so everything that we remove from here to here, so the integral below this curve, for different beam currents. This is now the strength of the electron beam, so the strength of the imaginary potential. This is what we remove, and the free graphs are for 3 different diameters of the electron beam. And you see that for the smallest 2 diameters, you can see an increase of the signal, and then the signal goes down. And this is the effect of the imaginary potential here. You can see it also here, and here it's maybe no longer really visible within the arrow bars. Now, the description, the orange curve that you see here, is a direct modeling of the time-dependent Grasp-Pitayevsky equation, where we put here the imaginary potential here. So you see that the imaginary potential in this mean field picture is a good description for this loss process. Now there is one additional thing I would like to tell you about this, and this is, if you look, we just take one of those curves here, we can divide it into 2 parts, because the beam current here can also be converted in a central dissipation strength, so this is the value given in kilohertz, and then we can draw another line, roughly, let's say, this is the blue dashed line here, and that is the time scale which is given by the interaction of the BEC. So it's a chemical potential in our case, and that tells you what is the strength of the unitary dynamics. And when you are left of this line, so it's a more qualitative argument here, then the H here, this is the chemical potential here, so what the quantum physics is doing is much more important than this one here, because the time scale for this is smaller than that, and this is why the unitary dynamics dominates. And on the other side here, when you want to see this effect that the reflection sets in, you have to overcome with your dissipation the coherent dynamics in the system in order to observe that, and here the non-unitary part dominates. So whenever you have the problem of seeing dissipation in your system in the one or the other way, it might be worth considering the situation where the dissipation is not as strong as the coherent dynamics, and you might still see some unitary dynamics, and I will show you an example for that at the end. So I also show you, we try to image the hole that we do, and I show you this was just a line scan taking after we have drilled a hole with the electron beam here. So this is roughly the electron beam, this is a density scan through the BEC, and here you see the hole. And I just want to point out, we also have some numerical simulations here of this Grasp-Pitayevsky equation, that you see that there are some wiggles on that, so it's not only just a simple hole, but it has some structure. And I will use this argument at the end once again. Now, in the second part of this talk, I will again consider a dissipative impurity, but now it is sitting on a discrete potential. It's a one-dimensional optical lattice, and each lattice side consists of about many hundred atoms, so it's a pure mean field problem here, and because the BEC looks like that, and the lattice goes in that direction, we have a stack of pancakes in this direction. And that system is very old in the field of ultra-cold atoms, goes back to early work in Florence, and is typically considered a Josephson junction array, so I've just coupled condensates. And we make the particular division of this system by choosing one of the central sites as our dissipative impurity, as our local lossy site, and the rest of it left and right as a reservoir of atoms where the atoms can go into this site here. Now, the first thing that I have to tell you in order that you understand the second part of this experiment is the precise microscopic physics, what happens at this tunneling junction between one side and another one. So normally if you have one lattice site and another one, you just write down a J, which is a tunneling coupling, and that is what you do with a Bose-Hubbard type of model. Here the situation is a bit more complicated because each lattice site here is in the transverse direction a two-dimensional harmonic oscillator. So it's not a single mode, 1D Bose-Hubbard model, not at all. It has many modes, and these modes have some radial extent. That is indicated here by these diagonal lines here. Now suppose you have the situation that you have a full lattice site here with a few hundred atoms there, all filled up to the chemical potential in this particular site, and you have this neighboring to an empty site. The empty site has no atoms, there is no interaction energy, the world exists only in terms of single particle states. Now the radial oscillation frequency of this two-dimensional oscillator is smaller than the chemical potential. It's much smaller than the chemical potential, about 8 states. Which means that if you were a boson that wants to tunnel from this full site into the empty site, first of all you have to obey energy conservation. And that's what you have to do. And then the consequence for you is that you have to tunnel into a radially excited state. You cannot tunnel into the ground state. Remember, it's empty. Because there's just this energy mismatch given by the chemical potential, because you don't have interaction energy here. You have to go in this state, and then what the basic result is that you get a reduced effective tunneling because your transverse wave function does not match. So here, in the full site, you have a kind of a mean field transverse wave function, which is a simple Gaussian wave function. But here, in the empty site, you have the Hermite polynomials of your harmonic oscillator, which are oscillatory, and that's why the effective tunneling coupling from here to here is reduced. And the essence is that the tunneling coupling J depends on the difference in atom number between the wells. If you have the same number of atoms in both wells, then you have the normal J that you can calculate. If you have a different number, the J becomes smaller. And this is now a consequence on the refilling dynamics. So we start with an initially empty site, and we just look how all the atoms fill up the neighboring sites. And you see, first of all, they fill up the sites. So this is the filling level over time. You see that for smaller tunneling couplings, here given the J over H bar, it takes a longer time, and then if you increase tunneling, it's getting faster. But what is more important is that you see these kind of, S-shaped behavior, best visible maybe at the red, at the blue curve. And we wanted to understand what this particular transport dynamics is, and that's why we convert this plot now in a current voltage characteristic, so in a transport characteristic. We take the derivative of the experimental data as the actual current, so the number of particles per time that move from the full site into this initially empty site, and then we also convert the actual atom number difference, because we measure the refilling here, so we know how full the site is, in difference in chemical potential. And then we interpret the difference in chemical potential as a driving voltage, and the resulting particle transport as a current. And the final result is that one here. This is now, if you look at this refilling dynamics, now you have to read the plot from right to left, because here the difference in chemical potential is 0, and here the difference in chemical potential is maximum. So which means here we go along this line here. This is the current versus the difference in chemical potential. You see, first you get a straight line. This is what you know from a resistive behavior here. More driving force, more current, but then it turns over, goes down, and this is then the appearance of negative differential conductivity. You increase the driving force, but you get less current. The reason is the intrinsic nonlinearity of the tunneling coupling. That is quite specific to this system. Okay, now that was kind of an intermezzo to now study what you have in analogy to the BC experiment that I showed you before, when you do exactly the same experiment in this one-dimensional Josephson array. So we consider this situation here. We have all the sides coupled to each other. We now remove atoms from one side. This is our dissipative defect. And just as in addition, we have a tunnel coupling that depends on the filling. Right? That's this J prime depends now on n, and this is the number of atoms here. This again was similar Josephson models have been studied before, but mostly in the context of the AC Josephson effect, where you see oscillations between S. What you see now is the realization of a DC Josephson effect. So if we now do the experiment, and we start again, as in the case of the BEC, we start with a full lattice side. This is the initial condition, and then we switch on the loss rating side. The question is what's happening. And the result is very trivial, but very surprising at the same time, because the result is that nothing happens, almost nothing. This is time now, 80 milliseconds, it's a long time. And you see that this is the filling level of this site when we start to remove particles, and you can see it just stays constant. So in contrast to the BEC case, there is no hole that we draw. Remember, in the BEC case it went down and then there was the steady state. Here it stays flat. Even though this looks boring, this is a very peculiar result here. And we wanted to understand it better. And first I want to state that there is a constant signal here within the arrow bars here. So there is a constant density everywhere, but don't forget we are removing particles from here, right? This goes on for another few 10 milliseconds, and then of course it goes down because the overall atom number is decreased. Okay, let's have a look at the underlying microscopic description. So I told you this is a Josephson array, so we can try to model it with a discrete nonlinear Schrödinger equation that you see here. So this is well known, this part here. You have, if you consider your lattice side psi n, then it has a tunnel coupling to the two neighboring sides, n minus 1 and n plus 1. It has an interaction energy because the atoms interact with each other. And now we have one loss rate here, given here with this delta function here. And the surprising thing is that, or not so surprising, but interesting thing is that indeed, for this type of discrete Schrödinger equation, you find a steady state that fulfills exactly what you need to describe the experiment. You have the same filling everywhere, so the modulus of psi n is equal to the overall, to the atom number in each side, and you have a finite phase difference between adjacent states. This is then a superfluid state, obviously, and it reads like that. That's the explicit solution for this steady state. And you see that the phase difference that you need in order to create the two Josephson flows from left and right is exactly depends on the loss rate gamma. So if you change gamma, you change the phase gradient and you adjust this superfluid current. You can also think of this in terms of a band structure here, in a single particle picture here. Initially, all your atoms are here at rest in the center, so you have no quasi-momentum. Now you start to remove atoms from the center. You get two input flows from left and right, and the group velocity of them simply depends on your dissipation rate. So the theory supports what you observe in the experiment. Now we observe here obviously a superfluid transport because we do not have any difference in chemical potential. We have the same feeling everywhere. Nevertheless, we see a motion of atoms. So that is superfluid flow here, and we can first test how long this superfluid flow survives. So what you see here is an increase in the dissipation rate gamma, so stronger and stronger loss, and this is the filling level. And you see that up to a certain critical value of gamma, we always observe the same behavior. It remains full, and then it suddenly drops down here. So there is a breakdown of superfluid transport somehow here. Now let's first also extract the current voltage characteristics, because when we look at the steady state, we can say that the change in atom number in this central site is given by the number of atoms that you remove minus gamma times the actual number that you have plus the current that flows from the side here. And in the steady state, this is 0, so you directly get the current that goes into the side. And now we have the current that flows into the side, and then we can also measure the difference in chemical potential by just looking at the difference in atom number. If the atom number is the same, we say the difference in chemical potential is 0. And you see that for all these points here, the difference in chemical potential is 0, but we see a current, so which pile up to this here in this current delta mu, current voltage characteristics, and then you see the other points down here with a finite difference in chemical potential, and it tells you that this is actually the same type of current voltage characteristics that you can also measure in superconductors. It's not so surprising because you have a superfluid, so you remove particles here and the superfluid can just flow without friction into that defect, and this is what we observe here. But there is more. Because we have an intrinsic nonlinearity in this tunneling junction, we can change the system by only changing the initial condition. So if we initially empty this side here, then we see some dynamics like that. This is now a single trajectory over time. This is the filling level of this side here. So it goes up to a certain point, and then again there is a steady state. Now there are several possibilities. This can fill up completely up to the upper part, and then you end up in the same situation as before. Then the initial condition is not important. However, you can also find situations like here, where for the same dissipation strength, the final steady state, these are two trajectories here, really depend on the initial condition. And that is intrinsic bistability in the system, then you can observe, which has its origin in this atom number dependent tunneling coupling. So here, if we just look at this part here, for this dissipation strength here, we can say that here, the superfluid response is very strong, and the loss rate does not manage to make a defect, to make really a density there, because the superfluid transport prevents this. But when you already have an empty side here, you have no superfluid transport anymore, because you have a difference in chemical potential. The atoms have to kind of somewhere go from here to here, but certainly not in a superfluid way. And that's why, for the same dissipation strength, you can keep the side empty by just removing this little amount of atom which goes into that side here. So there is the appearance of bistability, shown here, but there is more. And this is just, if you just look at this graph, you can, I argued a lot that when you see unit filling, you have a superfluid transport towards your dissipative impurity. But of course, if you have very strong losses, you end up in a situation where you have an empty side and a full side, and you have some atoms dropping there. And for sure, you would call this an incoherent transport, right? There is no defined phase or wave function, or you maybe do not even expect a condensate existing in this side. So if you just follow, for instance, the red line here, you must see a transition. And there is a star here, and the question is what happens there. Remember, this is now a regime where your side is partially filled. So it's not full, it's not empty, but it's kind of in between. So here it's superfluid, here not, so is there a phase transition in between? So what we have looked at is exactly around this point here, this is dissipation strength gamma, on the initial dynamics. How long does it take to reach the steady state? This is a measure of how important fluctuations in the system might be. And you see that the time scale on which you reach the steady state indeed diverges or becomes large at one point, and then it drops down. So it looks like, we have not a complete understanding of this, but it looks like a slowing down, and we speculate that this is connected to a phase transition to a Bose-Einstein condensate that takes place in this central part here, and that is an effect of, on the one hand, having the atoms want to condense, on the other hand you remove the atoms, but you have also a strong flow of atoms from the neighboring side here. What is important to know is that this happens roughly at a filling of 30-40%, but just from calculation you expect in equilibrium a condensate to form already at a filling level of 10%. So we think that this is a strong deviation from that because you have these strong losses. So you're far away from thermal equilibrium. Nevertheless, we think it is a phase transition, because also another indication for us is that if we sum up the density profiles on the left side on the red points and compare them to the density profiles on the right side here, the left side is the blue one, the right side, the red points is for this part here. You see the blue ones is a little bit smaller, and it is also compatible with the idea that for lower dissipation strength here we have a condensate. I mean, for these points for sure we expect to have a condensate. We find this for every dissipation strength. It's a quite robust phenomenon here. If the tunneling dominates, then there is always the superfluid transport in the defect. If, of course, the dissipation dominates, you expect just having low atom high number and some dropping of atoms, and in between we see these bistability regions. So at the end now I give you a completely, almost completely different interpretation of this superfluid transport in terms of what has been called coherent perfect absorption. This is something that was pushed forward. We have 2 slides, okay? That was pushed forward by Douglas Stone in 2010, and he was considering the question: can you make a perfect absorber for light? So is there something like an inverse lasing process that you send a laser into some media and you can be sure that 100% of the laser light is absorbed? That is what they call in their paper the coherent perfect absorption. And they come up with this setup here, and they also have studied this experimentally with a laser slab. And it works like that. It's easy to understand from a qualitative point of view. You take an absorbing medium that you have here, and you have incoming laser radiation from left and right. It also works with only one side, but here, to compare it with our experiment, we take it now having laser radiation from left and right with the same frequency. Now you have some mirrors here and here, 2 mirrors. And now what does coherent perfect absorption mean? It means that all the radiation that goes here in from both sides is dissipated here and does not reappear. So it's neither effectively transmitted nor reflected. So there is no part of the wave that goes out in this direction and in this one. And it can be realized because you can make an interference between the transmitted waves and the reflected waves. So consider now this incoming radiation from left. So you can say that after bouncing back and forth and being absorbed, there is a certain reflected part of this wave. And now consider the laser which comes from the right. After interacting here with that, there is a certain transmission of that. And if these two are out of phase and have the same amplitude, they deconstructively interfere, and at the end you are in the regime of this coherent perfect absorption. The point is that you have to match the mirror reflectivity and the absorption to the wavelength so that it works. It's not easy, so it just works for one wavelength, for instance. But it works, and they have shown that it works. Now, if you understand that, you can transfer this to our experiment here, because we have essentially a similar situation in a nonlinear medium. So we have incoming matter waves from left and right, which are given by the DC Josephson currents that we induce. And here we have an absorptive media, so we have a local loss process, and we have kind of 2, let's say, partially reflective mirrors, which are just the 2 wells. We only consider this part here. And I would just like to remind you that here we just see that there is a full lattice side here, so that there is no kind of density which goes out or which is referred to. This is also what the solution of the Josephson model tells you. But here is something different. I told you in the optics, it's not easy to make this. You really have to tune the mirrors and the absorption that it works. Here, it automatically appears. We do not tune anything. We just set one value of gamma, and then we end up in a state where everything that goes into the defect is absorbed. And the reason is that this is a nonlinear system here. And this nonlinear system has some attractor dynamics, and indeed this is the case for the Josephson model, because as soon as you increase population imbalance, you induce a current which is compensating this imbalance here, and that leads you that you automatically end up in this situation here. So here the perfect absorption appears for every gamma. We are now thinking more about this type of what in essence is this? This is describing this dissipative defect very much in terms of a scattering experiment, right? And we are now continuing to think about this direction and see what we can also learn about it if we look at it from this point of view. But this is the one I wanted to tell you. It is a kind of a new understanding of the same phenomenon. Okay, that was it. I would like to thank the people that are involved with that experiment. Currently, this is René Hamburger, this is Chen Xiang, this is Christian Wals, Andreas Müllers, and Jens Benari, and there are also many former group members who have been involved with that. And that's it. I thank you for your attention.
Thanks. Any questions? So, in the beginning you discussed these imaginary potentials.
Yeah.
How will it approximation is this?
You mean in terms of quantum fluctuations, yeah. They kind of spoil it? For sure, we don't see anything that comes from quantum fluctuations up to now, I would say. Also, in these, I mean, if you look at this type of, where you have a few hundred or 80 atoms per lattice side here, I would still say it is probably good described with the weak field theory, as at least in the superfluid regime. Certainly it will break down if you come to the few atom limit. But if this is 5, 10 atoms on a side already, I don't know. I'm trying to find if there is some basic argument.
It's like a continuous loss model.
Yes.
Rather than taking into account discreteness.
Yes. Maybe it's like
the chemical potential, for example, changes by adding and subtracting one or two.
Stronger than the loss rate. Maybe that would be such a time argument. Yeah, that the energy change in a fluctuation is comparable to gamma. Yeah, that would be an argument.
But you're far away from this.
At the moment, yes, I would say, yeah, we are.
A related question, or maybe the same question in the end, but so originally when you started from the open quantum dynamics, it satisfies fluctuation dissipation theorem, right? But in the end, when you go to the Crosby-Dayevsky equation with this imaginary term, it clearly violates fluctuation dissipation theorem, right? Because you only have dissipation, zero fluctuation. So it's the fluctuation. Isn't there any fluctuation from removing these atoms, or is the fluence of the electron beam so high that you can neglect it, or I don't know?
No, there are fluctuations. I think the point is just that we don't see them.
You don't.
In order to just the bare number of atoms with which the electron beam is interacting, the next point is, which makes it difficult to observe experimentally, that we do not see all the ions, all the atoms that we remove. So we only see a part of it. So even if we see, of course, we see fluctuations in the signal that comes out of it, but these fluctuations are mainly or maybe exclusively due to the detection statistics, and not to the statistics of removing.
Because usually it just induces phase fluctuations, and this could destroy phase coherence between left and right. That you can see. Well, you see superflow.
Yeah, exactly. So also the phase coherence remains the same between the two sides here over this time scale.
What is the key difference between the bulk VC and these lattice and pancakes? Does it just come down to this non-linearity dichotomy, or why do they really behave so?
So the VC is not a perfect absorber, obviously, right? You have a hole, and you also see in the simulation of the Crosby-Dayevsky equation that you can have reflected parts. I think it's the discreteness here that makes the difference. Because so you boil it down to a very simple 1D situation, and for that particular case you can see it. And only there. I think I'm not sure if this survives, for instance, in 2D. You can think about it. 2D area removing atoms there. I don't know precisely. We haven't looked into that, but I think it's that.
I think it's the next slide or so where you're measuring the that profile. That's the profile transverse to the lattice.
Yes.
Okay. Can you tell me about your estimate of that you should get filling at 10%? It's not obvious to me how you would model when you would form a condensate. There's a lot of different energy scales there, and
how we come to this number here that we
Yeah.
set the 10% to
Yeah,
see
the
the
prediction.
condensate?
Yeah.
Well, we looked into the 2D theory, in the 2D model of the lattice side with the appropriate oscillation frequency, and then we were calculating the phase-space density that you have, or how many atoms do you have to fill in there until you reach.
What are you assuming?
The condense-
What are you assuming for sort of the energy scale? The atoms that go in, they're tunneling in. They have lots of different levels.
No, this is just, we just consider one isolated site, and think of how many atoms do we have to put there until we reach the condition for condensation at temperature equal to 0. And that happens at about, I think, 80 atoms in the site. But a full site is about 800.
Any other questions? All right, thank you, Harvard.